We are now going to look at the structure of the atom. The atom is the smallest particle of matter that retains the properties of matter, the chemical properties of matter. The concept is rather old. It's been in different parts of the world. In the West, it's from roughly 400 BC by Democritus, who proposed that we cannot divide matter indefinitely, that there's a limit to how much we can cut down matter. And that limit was called the atom. And in more modern times, Dalton proposed a model of the atom, saying that again, there's a limit to how much we can cut down matter, and when we cut it down, we end up with the smallest particle being a tiny, indestructible, indivisible particle. And all of our elements are composed of these tiny particles called atoms. And then all the atoms of an element are identical, and that these atoms of different elements combine to form compounds. Compounds contain atoms in small whole number ratios. And if we change that whole number ratio between the atoms, we end up with a different compound. And in chemical reactions, the atoms are reorganized, changing the way they're bound together, creating new compounds. But the atoms themselves are not changed in chemical reactions. So this model, being just over 200 years old, is a pretty good model, except it did have some faults to it, as all models tend to. So the particles, the atoms, are not indestructible, indivisible particles. We have found that out, that we can divide them. We can pull particles out of these atoms. The particles that we pull out, called subatomic particles, no longer have the properties, chemical properties, of the elements anymore. So the atom is still the smallest particle of the chemicals, the elements that we know. We also know that we can destroy these particles in various ways, such as in nuclear reactions, nuclear reactors. Nuclear reactors destroy one element and create two new elements. And nuclear fusion also takes one element and converts it into another element. We also know that the atoms of an element have some variation in mass. Their chemical properties are identical, keeping them all part of an element, but they have variation in mass from a change in one of these subatomic particles. And the different types of the atoms of one element are called isotopes. Another model from Thomson was derived by his observation of cathode rays. Cathode rays are rays that come off of cathodes. Cathodes are a electrical terminal. We have anodes and cathodes, the ends of a battery. So we found that coming off a cathode are particles, and we can deflect these particles by magnetic fields and by electric fields. And by the movement, we can tell that they are negative particles, and they have very small mass to them. We call those negative particles electrons, and we give the symbol E with a superscript negative for electrons. So we see this small particle, smaller than an atom, coming off of material. From the anode, we've been able to get a positive ray coming off, called a canal ray. The positive ray was dependent upon what gas was present. And the smallest positive ray came when hydrogen gas was present. So the smallest positive particle that we found, we call the proton, give it the symbol P with superscript plus. So there's two particles now that we see inside or coming from the atoms, the electron and the proton. Electron is negative, proton is positive. They have the same magnitude of charge, electrical charge, but just different sign. But the masses are quite different. So electron, 9.11 times 10 to the minus 28. Proton, 1.67 times 10 to the minus 24. So rounding to magnitudes, the electron is roughly 10 to the minus 27 grams, and the proton 10 to the minus 24 grams. That's about 1,000 times difference in size. So the proton has roughly 1,000 times more mass than the electron. It's actually more like 1,800 times more mass than the electron. So the electron has very little mass, proton has a lot of mass. For the Thomson model, the electron came out easily. Positive charge didn't come out very easily. So it was viewed like the electron was embedded inside a positive atom. Rutherford changed this view with a scattering experiment. Don't have a picture of that. So in the scattering experiment, alpha particles, which come from radioactive decay, were directed at a very thin gold foil, and this gold foil had a screen around it so the location of the alpha particles could be found. And it turned out that most of the alpha particles went straight through the gold foil as if nothing was present. Only a small number of alpha particles were scattered around. So it appeared like there's a very small dense center in the atom, but the majority of the atom does not have much mass to it. So there's a very small high mass center in the atom, but most of the atom has almost no mass. Well, almost no mass corresponds to electrons. So Rutherford postulated that the small dense center contained the protons, and the majority of the volume of the atom was electrons with very little mass. So the alpha particles would fly right through the area of the electrons and would only scatter off if they hit the dense nucleus. So the very dense center is called a nucleus. And then a couple decades later, a third subatomic particle that was neutral was found. This is called the neutron. Its symbol is N with the superscript 0. And the neutron also has mass similar to the proton, and it's also found in the nucleus of the atom. So the nucleus of the atom contains protons and neutrons with almost all the mass of the atom, but most of the volume, almost all the volume of the atom is occupied by electrons with almost no mass. So in terms of size, again, the atom is about 1 times 10 to the minus 8 in centimeters, and the nucleus about 1 times 10 to the minus 13 centimeters. That's a 5-order magnitude difference. So the atom is about 100,000 times larger than the nucleus. The nucleus is about 100,000 times smaller than the atom. So our subatomic particles, we have 3 of our subatomic particles. Electrons, symbol E minus. It's outside the nucleus, has a charge of -1. This is relative charge. And then mass in atomic mass units is 5.5 times 10 to the minus 4 atomic mass units. So a very small amount of mass. Proton, symbol P plus, is found inside the nucleus. It's a +1 charge, relative charge, and a mass 1.0073 atomic mass units. Neutron, symbol N0, is also inside the nucleus, has 0 charge, and a mass of 1.0087. So the proton and neutron have similar masses, up to 3 significant digits. On the 4th significant digit, we start to notice a change in the mass of the proton and neutron, with the neutron being just slightly heavier than the proton. And the difference between the proton and the neutron we find when we look at radioactive processes. And in certain radioactive processes, a atom can swallow an electron into the nucleus, and when it does that, the electron combines with the proton to form the neutron. So neutron is really made from a proton combined with an electron, hence the slightly additional mass on the neutron. And we've said this already, the atom is roughly 10 to the minus 8 centimeters, the nucleus roughly 10 to the minus 13 centimeters, a 5 order magnitude difference, so that would be 100,000 times difference. So the atom is 100,000 times larger than the nucleus. So we have 3 subatomic particles. What defines which one's what the element is? What defines an element? Well, the atoms, the outside the atom and the majority of the volume of the atom is electrons. Electrons define chemical properties for us. It's really when we make a compound from elements, the electrons meet from the different atoms, the electrons interact, and the electrons determine whether bonding occurs. However, we find that since the electrons are on the outside, we can sometimes remove the electrons or add electrons in, extra electrons in, to create charged atoms, which are called ions. So we don't use electrons, the number of electrons, to define an element, since we can add or remove electrons. But in the neutral element, neutral elements have to be neutral, 0 charge. Bulk phase items are always neutral. So any bulk phase element is neutral. To be neutral, the charge has to be 0, so the number of electrons has to equal the number of protons. But the protons we can't change easily, not in any chemical reactions. We have to use nuclear reactions to change the number of protons. So we define our elements not by the number of electrons, but by the number of protons. Electrons determine chemical properties, but the number of protons determine how many electrons that we have in the neutral element. We use the number Z to represent the number of protons, which we call the atomic number. So atomic number is the number of protons in an element. Number of protons in an element define the element. So the atomic number defines the element.